In this video, we get to talk about the last couple of boxes here, all about ezGal, having to do with looking at the galactic plane and studying the galaxy. It reads the gal.npz data files that are created by ezCon. There are two ways to collect all this data. One is without motors. Let's take a look at that first. One would typically point your telescope to the south. That removes that third motion we talked about in the previous video, having to do with the Earth's rotation. That rotation would change the velocity your telescope sees when looking to the left or the right instead of looking straight ahead at south. Looking south along the meridian or even north along the meridian removes that third velocity to calculate. So we often look south 180 degrees in azimuth, and then we point the telescope at different elevations from the horizon at 0 degrees. In this example, LTO 16, the Little Thompson Observatory 16-foot big dish, pointed for a period at a certain angle from the horizon. Then it actually went down for a little bit, see how far down we could go. And then every week I would go out there and change the elevation by about 3 degrees. So after many weeks, eventually I got up as far as I could, looking vertically 90 degrees. I had trouble with the telescope bending over backwards and looking towards the north. And so I simply went down and looked at some other low elevation parts of the sky. When plotted on an azimuth and elevation plot, it looks pretty dull. It's got a whole bunch of points at 180 degrees on the south. They're all above the horizon, of course, and looking at several different elevations going up. For each one of those elevation changes, there's an equal change in the declination. The declination is a coordinate for the radio sky and the optical astronomy sky. It doesn't correspond to the telescope's horizon directly. There's a little math involved. Therefore, for each declination, we collected data along here, a big long line of power data stored away in computer files. ezRA will average those data points from week to week if they land on the same spot on the sky. We can see some bright spots here about where they should be on the sky, where the galactic plane is. Another view of this is with a vertical offset. The little green lines travel along where the average of the signal is, but if they have more power received, the green line raises higher, a vertical offset for power received. And we start to see bumps along again in the right places. We can plot little green dots where those maximums were. And that's true on both sides here. The red line represents the galactic plane where the galactic latitude is 0. We can take that same data and plot it on a galactic plot using galactic coordinates. 0 and 0 must be the center of the galaxy, is back behind this point someplace. So sometimes the telescope is looking above the galactic plane, and sometimes during the day it is looking below the galactic plane. That's what this plot says. For each sample, each vertical line going up and down, we have data points, little green dots, going up and down for the galactic latitude. If we take all those samples and order them in increasing value, we get a curve from low to high. But here, when we study the galactic plane, we only care about those samples near the 0 galactic latitude. How about those samples near the galactic plane from -20 to +20? They would look like this in the drift scans. We have values for every galactic longitude along here. It may not be very good. This is not very close to the galactic plane, but it counts. So this one trace coming down here would be in several different buckets in that gal.npz file because it crosses several different galactic longitudes left and right. Okay, if the criteria was plus or minus 10 degrees, we have fewer samples to choose from. For plus or minus 5 degrees, it might look like this. Plus or minus 2 degrees shows up here in the top left. 1 degree, how about within half a degree plus or minus of the 0 line galactic plane? We get a bunch of samples. Another way to collect data is with motors on your telescope so that you can track a particular point in the sky even as the Earth rotates. In that case, we don't care about azimuth and elevation directly. With tracking, we can start concentrating on galactic position in the sky. We care about along the galactic plane, and so all the data points end up to be a value of 0 because the motors made it so. If we look at what happened in azimuth and elevation, we can see that the telescope would track a certain part on the sky, maybe for 15 minutes, and record many samples of which to average the data. Then it would move to another point on the sky and study it for 15 minutes. If we look at it in right ascension declination, where I'm happy to see all the data points line up right along the galactic plane where they should be. How efficient. The red lines represent galactic latitude 0, the galactic plane, and the green dots show up right along where I told them to go looking for. Again, very dull plot in the galactic plane. All the data points show up along the galactic plane, just as requested. There are a couple of gaps, so I need to go back and collect some more data. Let's look at some of those results. The gal.npz records information for an average of many different samples sorted by galactic longitude. A positive velocity here means the hydrogen cloud was moving away from the local standard of rest. At a different galactic longitude, this time -141, 2 clouds are involved, and they're moving at different speeds along the line of sight of our telescope. Here we see 3 clouds moving at different speeds. And here we see even 4 clouds moving at different speeds relative to the local standard of rest. There are 360 degrees of galactic longitude, and you can get a plot for each one. Here's for 0, here's for 1, and we count all the way up to galactic longitude plus 89. ezGal provides 3 more pages of this. This is only the first 90 degrees. That's called galactic quadrant 1. If we take each one of these spectra and plot them together, we might see something like this. Down here at 0 on the vertical scale is galactic longitude 0's velocity spectrum. Sort of has two bumps. Behind it, one line up, is galactic longitude 1, and climbing all the way up to galactic longitude 90. That's the first galactic quadrant. We see interesting things. There's some RFI that shows up over here as kind of lines. There's kind of a big bump over here on the right-hand side with positive velocity. There's some big, long, curvy section over here on the left. There are 3 more quadrant pages just like this. If you combine all of them in one plot, you get something like this that provides from minus 180 degrees through 0 all the way up to plus 180 degrees of galactic longitude. We were looking from about here in 0. We see a big bump over here on the right, all the way up to about 90, about halfway up here. We now see, by adding the others, this ridge, this big long arch of negative velocity shows up. And there's something of a big triangle of energy in the plus side. Of course, there's a place where the data is missing, where my telescope could not see the galactic plane. If we take this section over here and rotate it over to the left, and down here on the bottom and rotate it over the right, and represent these bumps instead by increasing color, brightness of color, we can see another plot which is more traditional, looking like this. Again, on the 0 through 90, we see a great big triangle of positive velocity. From 0 through 180 degrees galactic longitude, we can see these large arches underneath displayed. Here's that RFI showing up as little specks of data. We can plot the average of each vertical line along here. And it looks something like this. Of course, there are places where I have no data yet. We can plot the maximum values for each galactic longitude. We can take that colorful plot we just saw and wrap it around a central point with galactic longitude being the angle used. In this case, increasing radius is increasing positive velocity. Here we can see the triangle on the positive side and perhaps the arches underneath here. But we could have plotted it differently, having decreasing radius representing increasing velocity. Here the triangle is on the inside and the arches are on the outside. This is closer to a plot that will come along later. If we go back to this original plot in color, how good is this data? How many samples have you averaged for the presentation? We can take that same information represented as color and use the galactic longitude as a plotting angle. We saw this plot before with the drift scans. Shown in red are the data points, the samples that met the criteria. This is for nearness of plus or minus 20 degrees. What kind of data do we receive? It looks something like this. I see data points all the way across for every galactic longitude. Looks a little fuzzier than before. I see something of a triangle, but I don't see any arches down here. This is the data for plus or minus 10 degrees of the galactic plane. Within plus or minus 5 degrees of the galactic plane, plus or minus 2 degrees of the galactic plane, we see a triangle showing up nicely up here on top. And now I start to see some arches down here below. Again, I was missing some information over here closer towards Polaris. Here's the plots for data within plus or minus 1 degree. And here's the analysis for data points within plus or minus half a degree of the galactic plane. We see a triangle here. We see arches down below, but there's some gaps in the galactic longitude data. I incremented the elevation by 3 degrees, and apparently that meant I skipped a couple of data points that close to the galactic plane. Here's the data from LTO 15, which had motors, which allowed me to collect more data. How does it compare to the plots of the professionals? This is crisper. We still see a triangle up here on the positive side. We see more detail in the arches down below. The triangle comes up, kind of has a flat edge on top, and then there's a faint part that climbs continually up and high, almost up to the value 200 kilometers per second. They have all the data, including the southern hemisphere, and so we see that it's symmetrical. There's a triangle on the lower side as well. I don't see as much arching on the right-hand side of the graph, though, but it is trying to be symmetrical. Sure enough, there's a triangle here. There's something of a flat top along here, and there's a faint whisper of a diagonal line going up. I see some arches down here. The professionals had more. On the right side, I'm missing data to see that full triangle. And it looks like some arches are trying over here as well. Well, okay, that's nice data, but what can you do with it? How about study the rotation velocity of the galaxy? You've seen this before. This was 4 different bumps of hydrogen gas emitting energy at different velocities along our line of sight. They seem to be increasingly traveling away from us, or at least from the local standard of rest. How is that created? This is those velocities over here, increasing different bumps along the way. With the galaxy center here in the middle in green, and the sun down below, we can see that all things orbit around the center of the galaxy. That makes sense. Let's assume that they're nice circular orbits because they've lasted a long time. We can measure the sun's galactic longitude angle by looking at the center of the galaxy and what is the angle to the left. That would be the line of sight of our telescope in this example. Let's study the sun first with its radius from the galaxy center. Along the orbit, there must be some gas far away that is also at the same radius from the galaxy center. And it must be traveling at the same speed around this racetrack as the sun is. So the difference in velocities along this line of sight for this of the hydrogen gas emission minus the speed of the sun's traveling along this line of sight should be zero. D should be a velocity of zero. Let's now consider B as in Baker, this red bunch of gas traveling around the galaxy center. All of its speed is directed directly along the line of sight. It would have the maximum difference between its velocity and the sun's velocity along that line of sight. A positive receding velocity is a positive number, and so B would win for the highest receding velocity. B would show up with the highest velocity on our plots. If we look at A or maybe C, we could see that it would have a velocity somewhere in the middle of those last two. Looking at this frequency, I cannot tell whether A is close to me or A is far away from me. And then lastly, let's look at E like echo here on the end. Its velocity is less along the line of sight than the sun's velocity along that line of sight. E looks like it's actually approaching us along that line of sight. It has a negative velocity. These are the spots of power we received along the velocity spectrum shown in this plot. Along each vertical galactic longitude data line, we're looking along a particular line of sight and seeing different responses from hydrogen gas along the line of sight. With trigonometry, we could decide a distance for the energies that were along the zero velocity. They would have the same radius as the sun. And those gas clouds that provided this top edge of energy would have a radius that is tangential to the line of sight. So we could, with trigonometry, we could determine its distance from the galactic center. Let's get those values and study them more closely. Those values are not black. They're not red. They're kind of in the purple. Way down here between black and red, down here in purple. Let's take a low number like 1.01. Find all the highest velocities with a value of 1.01. Okay, that's getting pretty close. We got dots kind of in the right spot. We got some other noise from our radio frequency interference, but that's okay. Let's try another number, not 1.01 with a 0, but 1.02. Ooh, that's getting just a little bit closer. Let's try 1.03. 1.04. I kind of like 1.05. That seems to collect the data points right along the edge where I was expecting them. Even shows a little flat top up here on top. But I also want to catch the data points for this spur going up to the right. So we're about at this data point here, going up to the zero longitude point up here, which is about a value of 160. Let's take a look at some galactic longitude here in the middle. That would be 45. This is about 15 or so. Oh, there it is, 1.05. And then starting at galactic longitude 15 and going up to a galactic longitude 0 value of 160. Well, that's not the point I wanted. I want the one up here, not down here. So I keep marching along, and I increased 15 all the way up to 22. 22 looked good. From here up to there seemed to be about where that spur was underneath. I'm collecting the data points along here instead of writing them down by hand. But what about this? That's that radio frequency interference. I'd like to have those 2 points down along with the rest of them down below instead of being up so high. ezGal writes out all these values in a file, and you are welcome to edit that file and then read them back in. So I could correct a couple of these points. Here's the data file copied to a new file name up here at the top. It has a list of a lot of numbers. You can see it started up here in the 20s, going down to 14, down to 6s, down to 4s. Every so often there's a comment line to tell you what galactic longitude is directly below it. Here's galactic longitude 60, here's 70, 80's down below. Going down the numbers, I found at 24, 24, 22, and then suddenly there was a 78. It was followed by another 78. So I put a bunch of comment characters in front of that value and inserted a value of 19. I put comment characters in front of the second bad value and inserted a new value of 17. Now it goes from 24, 22, 19, 17, 14. That's a better slope. The same is true down here. There are lots of 6.9s with a couple more 6.9s. And so I commented out this bad 78. And it took this number above and inserted it underneath. I took this number from below and inserted it below the bad number. And now the numbers climb along at 695, and that's a little smoother. I instructed ezGal to read from this new and improved file, and it looks pretty good. Here's the red lines coming, red line of dots coming along here with values. Let's use that for further calculations. The RFI spots are gone. If we look at just that top line in red, and then in the meantime, there's another blue line underneath here and over here on this side as well, all being calculated. It looks a lot like this. Now, how did I do all that? Let's review. We created an array of values for the velocity galactic longitude plot. We want the upper edge values, U for upper. I ran Python, ezGal, and then I requested the level value of 1.05 eventually. I climbed up from 1.01, you recall, each one with a 0 after it. When I decided 1.05 was good, eventually I changed that to galactic longitude 22 for the left part of that diagonal line, and then 160 for the value of that diagonal line once it met galactic longitude 0, that central vertical line. The keyword is ezGal, of course, velocity, galactic longitude plot, the edge level, and because it has a list of numbers, we have an L after it, meaning for list. I only cared in this case for plot 540, so instead of plotting all the plots, I requested of ezGal a plot range from 540 to 540, just to make it faster. Every time ezGal ran, it created a file for plot 540 called ezGal 540 edges. There was an upper one And there was a lower one. Here's the U for upper, file out.txt. Every time ezGal write runs, it will step on this file. So I better copy it to another name. I made a complicated name. You could call it Fred as far as I'm concerned. ezGal 540. And then I put the numbers in here that I had used eventually. .txt. I edited that file. You saw how I changed 4 values. I even left the original values in using comment characters. I used a whole bunch of comment characters. You could use one or just delete the line. And then I want to use this file with ezGal. ezGal, you run it the normal way. I'm looking at all the gal.npz files in the current directory. That's what the period stands for. And now a different keyword, ezGal 540 edges U file, much like the original file name that gets pumped out. This is where it would read in a new file. And then I gave the file name that I had created. So it wrote out a file, I edited it, and then I gave it a command line so that it would read in the new improved file. This is the plot it created for the gas maximum velocity around the galactic core, using these values for that top edge. It's a rather flat line compared to many. There's a part here that looks suspiciously straight. That was that diagonal line off to the right. I'll show you. And we're missing the RFI, but it has a value up here someplace, the maximum of 224 on the y-axis. And Wikipedia says the sun's velocity around the galaxy is around 220 kilometers per second. And that's about what this plot seems to say. But more importantly, it's the shape of this line as we increase in galactic radius. The sun is about 8 kiloparsecs way out here. Again, with that data correction, if I leave in the RFI data, it shows up as a couple of points way up here. And if I leave in, if I don't provide that diagonal spur off to the right, the data looks pretty confused. Even with this, we can see that this part out here just kind of seems level, way all the way out to the sun's radius. Is that what we expected? We can think of the planets traveling around the sun. As the planet's radius from the sun increases, we clearly see that the speed that they travel around the sun is slower and slower and slower. Long ago, Kepler could have created this plot using the mathematical relationships he discovered. Of these two plots, my data look more like B going up here, as opposed to the Keplerian rotation, which comes down and to the right. One method that professionals use to explain this flat plot along the top, B in red, is the presence of dark matter that we cannot see. And the professionals are having trouble explaining what dark matter really is. It seems to have a gravitational effect, but we can't sense it otherwise. We can also use that highest velocity information, that upper edge information, to study the mass of the galaxy. For a large center mass M, shown in green, with a small mass in a circular orbit of radius r, that's that yellow dot at the bottom, and using the gravitational constant, the large center mass M is described by the velocity v of the small orbiting mass. The large mass is equal to v squared times r over g. I have those r's, the radius from the galactic center, all the way up to the sun's location at 8 kiloparsecs. And I have those v's, the velocities. The data goes all the way up here. The measured maximum for that top point is about 914 times 10 to the 10th. But it's difficult to compare that to what the professionals say. There's a lot of different numbers. Wikipedia currently says 1.15 times 10 to the 12th. A recent paper from SOFU in 2017 says 1 times 10 to the 11th. There seems to be a lot of active professional research into the galactic mass, particularly after the new database release from the Gaia spacecraft. Now, this measurement does not include any mass beyond the sun's radius, and so it could be a little low, but 9 E10 is pretty close to 1 E11. So that's good. Well, how else can we use this data? With the sun at the center and a certain galactic longitude line of sight, what distances does that energy show up as? Where can we find hydrogen along that line of sight? For all these different angles along here, we know a distance of about how far the sun is away from the galactic center, shown in green, and so I put a green dot here as well. The data is here, but there are a bunch of holes in the data. Can we fill that in with a computer? Can it interpolate between these points and fill in a colorful dot where there is no dot now? We filled in some of the data, at least more points in the center. The sun is now no longer at the center of the graph. The galactic center point, wherever it may be, is at the center of the graph. What can you see here? We see that triangle we were talking about. It's on the inside now. There seem to be a lot of arches. Here's one about at the same radius as the sun. But there's another arch out here. There might be an arch on the inside. There's another one in here someplace. Can we plot the galactic arms with this information? This is my try. The center of the galaxy apparently has a bar, the professionals tell us. The sun is in yellow, and there are 1, 2, 3, 4, 5 different arms that perhaps I can see in the data. Let me flash back and forth, and you can make your own decision. And with all things about radio astronomy, always need better data and more data. Please give ezRA a try and send me news of your successes.